So, hi everyone. Today we'll be discussing about risk parity based portfolio optimization. Okay. So let us, first start with a short introduction of what portfolio optimization is. What are some traditional methods that can be used to, allocate your funds to certain, to fixed number of assets. Then we will discuss what are the potential problems, and then we will move on to risk parity based portfolio optimization, its mathematical formulation and numerical procedures. Okay. So let us just take an example in which you have n assets. Okay, so you have n assets and you have around x dollar. Okay, so now you want to park these funds into this n asset. Okay, so what are some common strategies that you can use to allocate your fund to these assets? Okay, so the first strategy can be you can allocate equal funds to all assets, right? So this can be one strategy to allocate. So the first strategy is allocate equal funds to all assets. Okay. The second strategy can be allocate fund according to market capitalization. Okay. So allocate fund according to market capitalization of the asset. Okay. Market capitalization of assets. So this can be the second strategy. Now the third strategy can be about MVO, right? Mean variance optimization method. So you can use MVO method as well to allocate your fund to these n assets. So one of the method can be minimum variance method, right? And the other method can be the MSR portfolio. So basically the maximum Sharpe ratio portfolio, right? Now all these methods that we have discussed so far now are traditional method, and they suffer from a drawback, and the drawback is these portfolios are not truly diversified. Okay, so these portfolio are not truly diversified. Okay, what do you mean by it? Okay, so let us take an example. Let us take an example in which you have a portfolio of 60% stock and 40% bond. Okay, now stocks are around 3 to 4 times riskier than bond. As such, 90% risk of this portfolio is coming from the stock. Okay, 90% risk of this portfolio is coming from the stock, and hence this portfolio is not truly diversified. Okay, this portfolio is not truly diversified. What is the reason behind this? The reason behind this is that the risk is often dominated by the stock portion of this portfolio, and hence we want our portfolio to be truly diversified. In that case, our portfolio should have equal risk contribution from different asset type. For example, let us say our 90% risk of, so let us say example in which the 90% risk of the portfolio is coming from the technology sector. Okay, technology sector. Now let us say suddenly the technology sector plunked down. So there is a huge crash in the technology sector. So what will happen? Your portfolio will basically get reduced to very 90%, right? So because 90% of your risk is coming from the technology sector, so your portfolio will suffer a lot. Because your risk is not diversified, because your risk is concentrated on some stock. So one of the serious drawback of traditional method is no risk diversification. In this chain, a new method, a new advanced technique is risk parity based portfolio optimization. Okay, risk parity based portfolio optimization. What does it say? It says that the risk contribution of all the assets in the portfolio should be equal. Okay, so basically the risk distributed equally among different assets. It means that, let us say the total risk of the portfolio is R and you have n asset, then the risk contribution of asset 1 is R by n. The risk contribution of asset 2 is R by n. So basically all the assets in the portfolio are contributing equal risk. So all the assets contributing equal risk. And this method is called risk parity based portfolio optimization. So in the risk parity based portfolio optimization, all the assets in the portfolio contribute equal risk. Okay. So basically risk contribution of asset 1 is equal to risk contribution of asset 2 is equal to risk contribution of asset I is equal to risk contribution of asset n. So all the risk contributions are equal, and when you will add all the terms, you basically get the risk of the portfolio, right? What is the risk of the portfolio, by the way? As you know, the variance of the portfolio is nothing but weight transpose into variance covariance matrix into weight vector, right? And therefore the risk would be nothing but the square root of weight transpose into weight matrix into W, right? So let us move ahead, okay, and try to see the mathematical aspect of the risk parity based portfolio optimization. So mathematical aspect, okay. Let us define few terms, okay. So first of all, the W is the weight vector, okay. So the weight that your portfolio should be assigned, okay. So W1, W2, W3, W, okay. And then you will be coming across terms like W sigma I square. So this is the variance of ith asset, okay. So variance of return of ith asset, okay. And this term will be the covariance, right? And then this term is basically the variance covariance matrix. Now your risk, basically the risk of the portfolio would be nothing but the square root of variance, right? And what is the square root of variance? This is nothing but omega transpose into variance covariance matrix into weight. So this omega is weight, basically weight matrix, okay. And it can also be written as summation for all I weight I square into sigma I square plus for all j not equal to I weight I into weight j into covariance of I and j. Okay. So now you may wonder, how did we write this? Okay. So we can, the first is you express this as a weight matrix. So you can look like this. So this weight matrix is W1, W2 to Wn. Okay. This one is the variance covariance matrix. So you can write it as basically this one is this. So this term will be the variance square. Diagonal term will be variance square. This term would be sigma 1 2. This would be sigma 1 2, right? And then this weight is another like the column vector of weight, right? So when you multiply, you get this term. So this is in another way to express the variance. Okay. Now, since this multiplication would be a bit difficult to interpret at this stage, I would just like you to walk through the two variance case. Okay. So the variance of the portfolio when you have two assets. Okay. In that case, the variance is nothing but omega 1 square sigma 1 square plus omega 2 square sigma 2 square plus 2 omega 1 omega 2 sigma 1. So this is basically nothing but sigma 1 2, right? So this is the covariance. So now you can see this is nothing but this term. So this term is the first term. So basically you are basically writing it as summation for all I. So basically for all asset I. So this is basically for asset 1 and asset 2, your weight square into their variance square. Okay, and this term is basically nothing but this one. Okay, so you are basically writing for all I, but so you are basically writing for all j, but not for that j for which j is equal to I. Okay, so basically you are writing for first of all I is 1, so you start for writing for 1, and then j is basically 1 in that case, but j cannot be 1, so j has to be 2 because j and I cannot be 1, so w1 w2, right? And then sigma 1, and then in other case I will be 2, and in that case j will be 1, so j will be starting from 1, so w2 w1 sigma 2 1, right? Then I is already 2 and j cannot be 2, right? Because j and I cannot be. So these two terms will be there. And when you sum these two terms, you will get this term. So basically, you can understand this term using the two asset case, right? So I just try to give you an kind of intuition on how this term came, basically. Okay. Now, I will be defining a very important term now. Okay. So that term is marginal risk contribution. Okay. Marginal risk contribution, so basically MRC. So let us first define it and then we will be seeing the mathematical formulation of marginal risk contribution. Okay. So the definition is it is change in the risk of the portfolio. So risk of a portfolio, it is change in the risk of a portfolio with respect to a small change in the weight of a component. Okay. So the marginal risk contribution of each asset component, weight of an asset. Okay. So weight of an asset, basically, that would be a better definition. So for example, you have an asset, then each of the asset will have its marginal risk contribution. What is meant by marginal risk contribution? So for an asset I, so let us say you change the weight of asset I to certain value, then what will be the change in the risk of the portfolio? So the notation is d omega I sigma omega. So it is basically marginal risk contribution of asset I, okay, is defined as this. Okay, so it is basically change in risk divided by the change in the weight of asset I, right? So the marginal risk contribution MRC, it is nothing but change in the risk of the portfolio. So the upper one is the risk and the denominator is nothing but the change in the weight. So marginal risk contribution is defined as the change in the risk of the portfolio due to a small change in the weight of the certain asset. So this is nothing but MRC of asset I, right? So what is MRC of asset I? MRC of asset I is the change in the risk of portfolio with respect to a sudden change in the weight of the asset. So in MRC gives you the change in the risk of the portfolio, right? Now, how will you evaluate this term? You already know sigma W, right? And you just have to differentiate it with respect to Wi, and then you will be getting it. I will be writing the expression directly. You can try doing it. So it will be Wi sigma I square, and then summation for all j not equal to I. Okay, omega j sigma ij divided by sigma. Okay. Now you may wonder how this term came up. Okay. So remember, this sigma omega is a square root term. So when you differentiate something like x square plus 5x, then you first have to differentiate the whole term. So this one comes under bottom, right? So that is where sigma omega is coming in the bottom. So you may try differentiating sigma omega with respect to basically omega I, and then you will be getting this term. Okay? So let us just try to see for a 3 asset case. So for example, for a 3 asset case, what would be the marginal risk contribution of asset 2, for example? So it will be defined as dw2 sigma omega. Okay? So here I is 2. So let us just write. So here it would be, the first term would be omega 2 square sigma 2 square, right? And then the first term is the summation for all j not equal to I. So let us start j with 1. So first of all, j is 1, right? So omega, so we are writing for asset 2. So it would be omega 2 sigma, I is basically 2. So basically we are writing for asset 2. Just a minute. J is basically 1. We will be starting from 1, right? So it would be omega 1. And sigma, I is basically 2 and j is basically 1. And then we will be writing for j equal to 2. But we cannot write for j equal to 2 because j should not be equal to I. Our I is 2. So we will be writing for j equal to 3 now. So it would be omega 3 sigma, I is basically 2 to 3. So the upper term we wrote, and this is the lower term. So this is how we can write marginal risk contribution. So this is the marginal risk contribution of asset 2. Similarly, we can write marginal risk contribution for other asset as well. Okay. Now, once we know the marginal risk contribution of asset I, we can know the total risk contribution of asset I. So the total risk contribution of asset I is equal to weight of asset I into marginal risk contribution of asset I. Okay. So this is the risk contribution of the asset I in the total risk. Okay. Got it? So what is total risk? Total risk will be, so let us first, this is the risk contribution for asset, right? So this can be written as Wi into, this is the marginal risk contribution, right? So it can be written as, so let us just multiply the above term. So it would be nothing but Wi square sigma I square. So we are multiplying the MCR with Wi, okay? Plus summation for all j not equal to I, omega j, so sigma ij divided. So this is the risk contribution for asset I, okay? Got it? Now, so what is the total risk? Total risk would be total risk of the portfolio. Total risk of the portfolio R would be risk contribution of asset 1 plus risk contribution of asset 2 plus risk contribution of asset 3 to risk contribution of asset N. Okay, got it? Now, let us get back. So this was some kind of mathematics that were required. Okay, so let us start. First of all, if we revise a bit, so we know about marginal risk contribution. What is marginal risk contribution? Marginal risk contribution is marginal risk contribution of asset I gives you the change in risk of the portfolio if you change the weight of asset I by certain amount. Okay. Now, if you want to find out what is the risk contribution of asset I in the portfolio, then you have to multiply the weight of asset I by the MCR of I. Okay. So this gives you the risk contribution of asset I. Okay. Got it? Now, let us get back to our goal. Okay. So what is our goal? Our goal is to create a portfolio in which all the assets, so our goal is the risk parity portfolio, right? Our goal is risk parity portfolio. And what is risk parity portfolio? Risk parity portfolio is a portfolio in which all the asset contributes equal risk. So our goal is RC1 equal to RC2 is equal to RC3 to RCN. So all the assets should contribute equal risk to our portfolio. Okay, got it? So this is our goal. So let us define our problem statement. So what is the problem statement? Our problem statement is we want to find weight W. So we want to find what weight should be assigned to different assets of the portfolio in such a way that First of all, the first constraint is the weight of the asset should lie between 0 to 1, right? The second constraint is that the summation of all weights should be equal to 1, and the third constraint is basically the risk contribution of asset I should be equal to risk contribution of any asset J for any I and J in the portfolio. Okay, so risk contribution of all the asset should be equal. If we try to write out like in other term, so it is nothing but what is risk contribution of I? So it is basically weight of I into MCR of I, right? So differentiation of I is equal to weight of asset J into MCR of asset J, right? So it is J over here. So this is their problem statement. So this is what we want to find out. Okay. So let us try to see an example and then we will be able to do it. Okay. So let us do an example. Okay. Example. The first example is we are trying to see two asset case. Okay. Two asset case. Okay. So in this case we have two assets, so our weight vector will definitely be W1 and W2. So we want to find W1 and W2, right? Got it? Now first of all, let us find the risk contribution of asset 1. What is the risk contribution of asset 1? So we know the risk contribution of asset 1 will be weight of asset 1 plus marginal risk contribution of asset 1, right? So this is the risk contribution of asset 1. Is equal to W1 into what is the marginal risk contribution? We know its formula, right? So let us write the MCR formula. MCR is nothing but weight I into sigma I square plus summation for all j not equal to I Wj sigma ij divided by sigma w. So this is the margin. So for two asset case and for our case I is equal to 1, right? So we can write it as W1 into sigma 1 square plus j would take two values 1 and 2, but j cannot be equal to I, right? So I in our case is 1, so j can only be 2. So here, so the second term will be W2 into sigma I is 1 and j is 2 divided by, just a minute, Wi into, this is the risk contribution. So now if you multiply it, so this is W1, right? So it would be W1 square sigma 1 square plus W1 W2 sigma 1 2, right, divided by sigma W. So this is the risk contribution of asset 1. Now what is the risk contribution of asset 2? It would be nothing but weight of asset 2 into MCR of asset 2, right? So it will be W2 into, if you write MCR, I is basically 2 in this case. So it's I2 square, W2 square into sigma 2 square plus j can take 1 and 2 values. So we have to sum for all j. So j can be only 1 and 2 because we have two assets, but j cannot be equal to I, right? I is 2 in this case. So j can only be 1. So here in this case we can write W1 into sigma, it is W1. Sigma I is basically 2, j is basically 1 divided by sigma W. So in this case it will be W2 square sigma 2 square plus W1 W2 sigma 2 1 divided by sigma W. Okay. So this is the risk contribution of the second asset. Now what is risk parity portfolio? Risk parity portfolio is nothing but a portfolio in which all the assets should have equal risk contribution. So this is the risk. So sigma W is the total risk, okay, and this one is the total risk contributed by the asset I. So the top one. So this one is the risk contributed by asset 1, and this one is the risk contributed by asset 2. This one, okay. So now according to this parity based portfolio optimization, RC1 should be equal to RC2, right? Then only the asset should have equal risk contribution. So W1 square sigma 1 square plus W1 W2 sigma 1 2 divided by sigma W is equal to this term, right? Sigma 2 square sigma W2 square sigma 2 square plus W1 W2 sigma 1 2 this term basically cancel out, then this one will be equal, because you know sigma 1 2 and sigma 2 1 is basically equal, so covariances are basically equal. So this can only happen when w1 square sigma 1 square is equal to w2 square sigma 2 square. From here you can write w1 square sigma 1 square, and then w2 can be written as 1 minus w1 square. So now you can solve this equation to find the value of w1, right? So from here you can get w1 is equal to nothing but 1 by sigma 1 divided by 1 by sigma 1 plus 1 by sigma 2. Try to find out it on your. And now once you get w1, w2 is nothing but 1 minus w1, right? So w2 you will get as 1 by sigma 2 divided by 1 by sigma 1 plus 1 by sigma 2. So this is the weight. Assign this weight to asset 1 and this weight to asset 2, and then you will get a risk parity portfolio. What is it? So then all the assets, so both the assets will be contributing equal risk to your portfolio. So this is the concept of risk parity based portfolio optimization. Let us take one general case. Okay? So what general case? Okay, general case. General case in which you have n asset. Okay, and in this case you are making basically one assumption. The assumption is, so you have n asset and the assumption is equal correlation rho. Okay, so what is correlation? Let us discuss it. What is meant by equal correlation? So basically, see, when this is the covariance, right? This is the covariance term. So basically, you can write covariance as rho ij. So this is the correlation into a standard deviation of I into a standard deviation of j. So now basically, this rho term would be different for different I and j. But here you are given that for all I and j, rho ij are basically same. So basically, it is equal to rho. Okay. Got it? So basically, you can write any covariance I as rho, a standard deviation of asset I into a standard deviation of asset j. Rho will be basically constant. This is the assumption. Okay. And you have basically an asset in your portfolio. So let us start deriving the weight. Okay. In this case. So now, in this case, what would be the risk contribution of asset I in this case? So let us try to find out. RCI would be weight of asset I into MCR of asset I, right? Got it? Weight of asset I into MCR, weight I into sigma I square plus summation for all j not equal to I, weight of j into covariance of ij, right? Divided by. So now once you multiply it, you will get weight of I square sigma I square plus for all j not equal to I, weight j, rho ij, right? Divided by. Now you can basically write this term. So basically, the covariance term can be written as weight I, weight j. Covariance term can be written as rho into this equation, right? So the correlation into the standard deviation, right? This is a constant, so we can take it outside, divided by rho w. So it would be weight I square into sigma I square, okay, plus rho is the weight that can be taken outside, into summation of j not equal to I, weight j, sigma I, sigma j, okay, divided by. This is the risk. We are calculating the risk contribution of asset I, okay, is equal to nothing but. Let us try to. This term that you are seeing is for all j but not equal to I. Okay, so let us extend it for all j. Okay, so let us extend it for all j. So now it would include j equal to I as well, right? So now let us subtract that term that we have included. So we have subtracted that term in which j is equal to I. So basically we have to subtract this term. Why we have to subtract this term? Because we have included it here. Earlier it was for all j not equal to I, but it is for all j now. So we have included one extra term in where j is equal to I. So we have subtracted this term here so that it becomes equal. Okay. Now this would be weight of I square, rho I square plus with the, let's take this term and this term here. Okay, so it would be minus rho weight I square, rho I square, sigma I square plus for all j weight of I, weight of j, sigma 1, sigma j, sigma I and j. Got it? Now basically what you can do, see, we can take this term as common, so it would be 1 minus rho, right, and then 1 minus rho I square, sigma I square plus rho weight of j, wi wj weight of. Now you see this wi is a constant. For example, we are calculating it for a constant I, right? So we can take wi rho I constant outside. So we can take basically wi rho I outside. Okay, so it would become 1 minus rho wi rho I. Got it? Plus we have a rho over here. We have for all j, wi is taken outside, it will be wj rho j. Okay, got it? Divided by rho w. So this is the risk contribution of asset I. Okay, got it? So basically this is the risk contribution of asset I. Just a minute. It would be summation. It would be nothing but wi. So it is basically risk contribution of asset I. Now when you equate the risk contribution of asset I to, so basically see, there are basically two terms over here. Okay, so this term and this term, and then we have this term. So now when you are trying to find out what is the portfolio that is giving you the equal risk, so basically you would be equating the risk contribution of asset I. So basically what you will be trying to do, so basically you will be trying to equate the risk contribution of asset I to risk contribution of asset j for any value of I and j. You already know the risk contribution of I, right? You can calculate the risk contribution of j and you can try to equate them and you can find the weight wi in this case. And then you see the weight I in this case would be nothing but, you can try to derive it, it would be summation this one divided by this term. So it is nothing but 1 by sigma I divided by 1 by sigma 1 plus 1 by sigma 2 plus 1 by sigma 3 plus 1 by sigma n. So this is the n asset case in which we have assumed same correlation for all the assets. Now you see in this portfolio optimization method, if you assign this weight to asset I and for example wj, so you can get, so for 1 2 3 4 for different value of I you can get weight, right? So now if you assign this weight to your asset, you will get a risk parity based portfolio in which all the assets will be contributing equal risk. So basically risk contribution by asset 1 equal to risk contribution by asset 2 equal to risk contribution by asset 3. So that is it in the today's lecture, and in the next lecture we will be seeing how we can extend it for other cases, and then we will be seeing the numerical solution method that we will be using for a general case, very general case, in which no assumption will be made. Okay. So if we summarize the today's lecture, we started with the definition, what is the problem with the traditional method, and then we saw what is the use of risk parity based portfolio optimization. In the risk parity based portfolio optimization method, all the assets contribute equal risk, so basically your risk is diversified. Okay. And when you, so now we see the technique how to do it. So basically we first define marginal risk contribution. Okay. After we define marginal risk contribution, you can get the risk contribution by any asset I. The risk contribution by any asset I is nothing but weight of asset I into marginal risk contribution of asset I. And now you just have to do one task. You have to equate all the assets. So for example, RC1 equal to RC2, and then you try to find out what is the weight. So your goal is to find the weight matrix. So when you equate it, you get the weight matrix. Okay. So that is it in the today's lecture. In the next lecture, we will be seeing one more case, and then we'll be move on to numerical method. Okay, and that will be the end of risk parity based portfolio optimization.